Welcome to this hands-on lab where we'll be building your first end-to-end machine learning project from scratch. Perhaps you wanted to build a complete project but felt daunted by the complexity. In this session, we'll demystify that process for you. We'll start by ingesting data into Snowflake, perform data prep, build and track our model, and finally deploy it as a REST endpoint in an interactive data app, all within a single streamlined workflow. Before we proceed further, here's a disclaimer. Perhaps a little background about me. I'm Chanin, Nantasenamat, and I'm a senior developer advocate at Snowflake. Before joining Snowflake, I was a university professor in bioinformatics, applying my PhD in machine learning to computational drug discovery. I also teach AI and data on my YouTube channel, Data Professor. Today, I'm excited to walk you through the process of building a complete machine learning workflow right here on the Snowflake platform. So, why Snowflake for machine learning? Because the platform is tightly integrated with your data and it delivers four key benefits. First is scalable. Cloudbeds, for example, achieved 95% forecasting accuracy on a massive dataset. Second, it's flexible. This allowed Zscaler to cut their model production time down to just 1 hour. Third, it's cost efficient. By eliminating data orchestration, Coinbase reduced deployment time from months to hours. And finally, it's trusted. Scene Plus used our unified governance to cut their time to production by 60%. This integration delivers real world outcomes. It's faster, simpler, and more governed. ML in Snowflake is all about flexibility. You can build models using any open source package, either pre installed libraries like XGBoost and PyTorch, and also scikit-learn, or you could pip install anything from public repositories and from PyPy, and also your own private repos. Then you can perform inference with any model directly on your Snowflake data, whether it's trained in Snowflake, imported from external platforms like SageMaker and Azure, or pulled from a model hub. For this demo, we'll use a multimodal bear dataset. By multimodal, it means that we'll be able to leverage both data and images for 200 brown and black bears, evenly split across four species like grizzly and Kodiak, with 50 instances each. The dataset combines images with six tabular features, making it perfect for tasks like image classification and data fusion. So you'll be able to combine all of these together in your inference. Here are some QR codes that you could use to retrieve the code, the data, and a quick start guide that you could reproduce and follow along. Snowflake ML integrates your entire end-to-end workflow in one place. You can develop in notebooks or external IDEs and manage the full lifecycle from experiment tracking and feature stores to the model registry and scalable deployment and serving. And now it's time for the demo. Before we begin, let's have a look at the data set that we're gonna be using today. And the data set is called the Bear data set. And it's not actual research or experimental data set. What I've done was I've used Gen AI to help me prepare the Bear data set, but it tries to mimic the actual physical characteristics of the bear as much as possible. So to make this data a bit more challenging, what I've done was selected brown and black bears for the study here. Why brown and black bears? Because they're quite similar. Some black bears are brown, dark brown, and brown bears they have different shades of color. There's going to be a total of four bear species that are the American black bear, Eurasian brown bear, grizzly bear, and the Kodiak bear. And to the right, you're going to be noticing the genus species name of the bears. So let's have a look at the data set here. So we're going to provide the data set here as the bear raw data, and it's going to comprise of a total of six features, and then the ID and the species of the bear. And so the six species, the six features we're going to use for the classification purpose. So it's going to be the unique physical characteristics of the bear that will allow us to essentially figure out which bear it is based on the six features here. But to make it a bit more fun, I mentioned briefly that the dataset is multimodal. So we're going to also leverage the image data here as well. So there's going to be a total of 200 images of the bear. Here's an example of some of them. And each of the pictures or images will feature the bear. And they are all generated by GenAI as well. And before getting one image generation, what I did was once the image is generated, I'll feed the image back into the GenAI and ask it to figure out which is the proper characteristic of the bear. Like what is the fur color, what's the paw pad texture, and it's able to do so. And if not, then I'll repeat the process of the generation again in order to ensure that it does. So we're gonna see here that we have the paw pad texture, we have the facial profile, and we also have the fur color. So the full data set is in beardata.csv file, as you'll see here. What we're gonna actually use in Notebook is only the bare raw data, which will not have the categorical variables. So you're gonna notice it has only the numerical variables here. And then we're gonna predict or classify based on the features that we feed it with. The model will associate the features with which bear species is it? Is it a grizzly bear? Is it a Kodiak bear, Eurasian brown bear, or the American black bear? And so there's a total of 200 of these. And then the images are provided in the images subfolder here. Also 200 images here as well. Let's have a look at one of them. And it looks pretty realistic though, right? So yeah, we're gonna be using this, and I hope it'll be fun for you guys to try it out. And we are also sharing the Snowflake demo notebooks here as well. So there's a total of 4 notebooks and 1 data app that we're gonna be building in this 1 hour's bootcamp workshop. You could download it by clicking on the notebook that you want to download and click here, download raw file. So I'm going to download one of them, and then you could repeat the same thing for the rest. Part 1. Okay. But actually, let me show you importing the notebook again as a container. So once we select the data file, the IPython notebook, if we want to run the container, you could just click on it. And then as always, select the database, the schema, and then you could use the CPU and click on create. Okay, so this is the copy. So let's just run with the copy here. All right, so I've heavily documented the entire notebook so that it'll be a bit easier to follow along. So the entire course content, as already mentioned, we have 4 notebooks and 1 data app that we're going to be building. And the first step, or the first notebook, which we are opening right now, we're going to ingest data, perform data wrangling, and then write the data to Snowflake, to a Snowflake data table. And then for the entirety of the remaining notebooks and data app, we're going to perform exploratory data analysis where we're going to get to know the data a bit more. We're going to then build the machine learning model. We're going to start by using several algorithms. We're going to use logistic regression. We're going to use the random forest, which is my favorite. And also we're going to be using the support vector machine, which performs really well, but it's a black box, meaning that you don't really know what's happening inside. In step 4, we're going to perform model tracking, experiment tracking of the model, where each parameter set that we're using, we're going to lock that to Snowflake. And then at the end, you'll be able to see all of the visualization or the data table, the summary of it, right in Snowflake, kind of like a dashboard where you could explore the performance metric and which hyperparameter give rise to specific performance. And at the end, we're going to create a kind of like the capstone project. We're going to create a data app that will allow the user to make a prediction based on the feature that they select. This is what we're going to cover in this particular notebook. So we're going to start by loading in the data, prepping the data, and then performing some basic statistics summary. And then we're going to do some feature distribution analysis to get to know the data a bit more. We're going to do correlation analysis to see which feature has correlation, inter and intra correlation with one another. And then we're going to perform some categorical analysis of the distribution of the categorical features, the one derived from the images. So go ahead and click on Start to start up the notebook. And if you like, you could just click on Run All, and it will run all of the cell in sequence, as shown here. So to the right, you'll see that it has all of the cell names. And what I've done was, instead of leaving it as cell 1, cell 2, cell 3, cell 4, was to name the cells according to the content that it has. So if it starts with MD, it's a markdown cell. If it starts with PY, it's a Python cell. And if it starts with SQL, well, you guessed it, it's a SQL cell. So give it some time for it to initiate. And because this is the first time that we're actually creating this container, it might take a bit more time. Okay, now it's active. And if you hover over it, you'll be able to see the hardware configuration. You'll see that it has 3 virtual CPUs, and we're using just 20% of it. And then we have a whopping 13 gigabytes of memory in here. And it will time out after 1 hour of idle time. So let's begin. So you want to set up your notebook for success. And what you could do is, if you're using a container, which we're using right now, everything is already all set. It's already configured for you. If you're using the one on the warehouse, then you might need to pip install or actually select from the packages here and then enter the name modin. And I think scikit-learn is already pre-installed for you. So yeah. And in a container, if you want to pip install anything, you could do so. So we're all set here. And let's go ahead and configure the notebook settings. So first step here, click on the 3 dots on the top right-hand corner, which is right here. And then we're going to run on container and compute pool, choose a CPU compute node. Okay. We have already done so at the first step. So what this means is that you could change the configuration of your notebook that you're running on. If at any point, if you created a container and you want to go back to a warehouse, you could do so. Or if you create a CPU container, you could change it to a GPU container as well. So we're not gonna do that. So we're gonna click on cancel. So it's very flexible. Okay, so in the third step here, we're going to activate the external access configuration so that it will allow your notebook to access resources outside this environment. So it's all about security. So we're going to click here on the external access and then scroll down, and then we're going to essentially activate all of the external access that we need. So we're going to activate the PyPy access integration here. We're going to allow all of them here. Everything external. Okay, so these policies were created by us manually. So you might have to do the same as well. Just wanted to make sure that I've activated all of them that we need. Okay, and click on save, and then the notebook will restart again. So give it a short moment. So we're gonna load in the tabular data set stored in the CSV file for the 200 bears. I already covered the essential features of the data sets. So once it starts up, we're going to load in the CSV data from the repository here, and it's ready. It's having this green indicator active. Go ahead and run the cell, and it tells you how many seconds that this particular cell is running. And it's going to be stored in the df variable, which looks like this. So you're going to see that we have the 6 features of the bear. we have the ID and the species of the bear. And in the next stage here, we're going to load the images into the Snowflake platform. And we're going to do that by creating a stage. And the stage is kind of like drive D, or kind of like a hard drive space on your own local computer where you store images, store files. But this is for Snowflake. So we're going to make sure that we're using the Chanin and demo data database, and we're going to make sure that we're using the stages schema. Go ahead and run it, and this should take only a few seconds. And if you get the statement executed successfully, that's a good sign. And then we proceed further. Now we're going to create the stage, and we're going to activate the server-side encryption to be true. And we're going to also activate the directory option here so that it will be able to allow us to see the files that are stored in the stage. And so it has already been created, and we're going to list the files in the stage called bear. So we had created a stage called bear, and we add the at sign here. So we're going to list the files in here, and you'll be able to see that the bear is in a folder called bear, and then we have all of the images along with the size and MD5 checksum data, and also the date of last modified. Now we're going to take a look at the images that are stored in the stage. So we're going to start by running the cell. And here we go. We have the bear images. And we're using Streamlit to display and organize the images here. And you'll be seeing that we're using the columns, the st.columns feature, where we created 4 columns and then inserted the images using st.image, and then the image of the bear. Okay, so this is not actually the images stored on the warehouse on the Snowflake stage, but they are derived from the repo that we host the data sets. But we're gonna use the images for the analysis, where we're going to extract features, categorical features, including fur color, facial profile, paw pad texture, directly from the images on the stage. And we're going to do that by using AI Complete, which is Snowflake Cortex AI. And we're going to use LLMs to extract the features from the image. And that's why we call it the multimodal, because we're using both the text base and also the image base for LLM analysis. All right. So our prompt was, what is the fur color of the bear? And then we selected the Claude 3.5 Sonnet model. And then the bear image was ABB01, which corresponds to the American black bear. And as you see here, the bear in the image has a brown fur color with some variation in shade. It appears darker brown in some shades and has a slightly lighter, more cinnamon colored patch on its chest. This is typical coloring for a brown bear, also known as grizzly bear. So you're going to see that because of the different shades of color, it makes this data set classification a bit more challenging and more fun. So we're going to do the same thing, but then we're going to implement it in a Python code block here. So the above was implemented in SQL, and it's only 3 lines, right? So you could leverage LM multimodal capability directly in SQL. And now we're going to do the same in Python. And the great thing is we're actually using the variables stored separately, and then we're injecting it through the F string in order to allow it to dynamically update the prompt and the image name. And now we're performing the LM inference, and wait a short moment. And here we have it. We got exactly, similar results, and the output is provided here. And now we're going to make it a bit more specific to our use case, where we're going to provide it a list of colors, and then the LM model will then select one of the options here and provide us and return us the output. And we're explicitly telling it to respond with a single value. So here, it's going to respond with a single value from the list here. So let's run it. And you're going to see that it will take a few seconds for this. And we have 200 images. But we're not going to do all 200 images in this workshop. So we're going to do a few so that you get the feel of it. And then you could perform the rest separately. So here it takes 23 seconds for one image. And we have 200 to go. The great thing about this is that you don't have to perform LM inference or generate the image or extract it on different platform and then save it, import it into your data platform. With Snowflake here, what you're essentially doing is you're feeding in the data, whether it's tabular data or images, and everything, including the LM model inference, the machine learning model building capability, model serving, all of them is directly in this single platform. So it makes it a bit more enjoyable and less shuffling of data, which might be a headache. So we're going to do iterative image analysis where we're going to leverage the power of the for loop um, to allow us to iteratively perform the same thing of extracting the color image, extracting the paw pad texture, facial profile of the bears automatically. So we don't have to run this 200 times. And it's provided here. So we're going to run it for a few cycle. And once you see it and get the feel of it, we're going to stop it. And then we're going to proceed further. So this is similar to the one mentioned above. We have the prompt. We got the list of files, the list of image files, and then we're going to create an empty result list where with each iteration, it will append the results to the result list. And by the end of the entire workflow, you'll be able to have a list of 200 colors of the fur color. And then for each image, it will print out the output and you'll be able to see it real time, the progress and how far it is performing on your data. So for the 200 images, it took a while, right? So you could, essentially brew coffee and come back and it should be ready. But we're not gonna do that. So we're gonna breeze through. So we're gonna stop that for a moment. And then we're gonna use the one that we have already pre-computed to proceed further. So let's see if it has some data here. Okay, it has 4 cycles. We had already completed 4 cycles here. And so what we got was the image name and also the corresponding color. So for each of the bear species ID, what is the color, the fur color? So in this step here, we're going to remove the PNG at the end so that we get only the ID and the color. And now we're going to convert the data. We're going to convert it into a data frame. So we have 2 columns, ID, color. And then we're going to perform the same exact workflow for facial profile. Let's run it a few times. So we essentially aggregated all of the cells above into a single cell, and then we're performing it all here. Okay, so the first bear, the facial profile is straight. Okay, and so we're going to skip the rest and proceed further. And then we're going to perform the image analysis for the paw pad texture. Just run it. So it's the paw pad, right? Whether it's more textured or less textured, And depending on which, it will allow the bear to have better grip for climbing, or if it's smooth paw pad texture, it's good for walking. So here we have a few inference from the model, and then we're gonna stop it. And we're gonna use the one that has already been pre-computed for you. So we're gonna load it into 3 variables: DF fur color, DF facial profile, and DF paw pad. So each of these will then be combined with the 6 characteristics of the bear to get our full data set. And then we're going to combine it. All right. We got the combined data here. And here it has written the data to a bear table. And the bear table is located here, the database called Chanin and demo data, in the schema called public, and the table called bear. And we have the data here. And so this is step 1. So give yourself a good pat in the back. You've done step 1, and then we're going to perform step 2. So now we already have the data in Snowflake. We're going to explore the data. And you could do the same thing, download the Jupyter Notebook file, IPYNB, and then import it into the environment. To save us time, we're going to skip all of that, and then we're going to proceed further with running the tutorial here. So here we're going to perform EDA analysis, exploratory data analysis. As already mentioned, we're doing summary statistics, and then we're visualizing the various distribution of the features. And here we're using a warehouse, so you want to make sure that you have Modin installed and scikit-learn. And if you click here, you'll be able to see that we already have done so in our prior session, in my prior session. And for your first time, make sure that you enter the name like Modin and then click on it, and then enter all of the packages that you'll need, and then click on save. And then your notebook should refresh. And now we're going to load in the data. We're querying the data that we have already saved from part 1. Now we're going to do the same in Python. And then we're going to store it in the df variable. Now we're going to show you how to do it using Modin's read Snowflake, which essentially does the same thing. And now we're going to perform some data prep where we're going to select only the numerical feature. So it's not going to include the categorical features here. And we're going to have a look at the feature distribution. And this is like the traditional way where if you're not using Streamlit, you're going to use the print command, and then it will be displayed here in, in the old-fashioned approach. And if we're implementing Streamlit, which is, I think it's the pretty cool web app framework, you could select a variable that you like and click on it, and then you get a tailor-made plot just for you. Click on body mass, and then it will generate another data plot. And let's have a look at the feature correlations. So we're going to perform feature correlation where we'll be able to visualize whether it is a positive or a negative correlation between each of the features that we have, the numerical features. So you're going to see that we have 6 numerical feature, and then depending on the value, if it's orange, it is a positive correlation. If it's blue, it is a negative correlation. And you could change the color scheme to another color of your liking. And here we created a list of color, but then owing to the old-fashioned approach that I'm going to show you as an example, we're going to select only the first element, which is blue-orange. And you could change that to another color if you like. About 11 seconds. Okay, there you go. And then you have a different color heat map. And we're going to implement that same thing, but then using Streamlit. So we're adding a spinner to allow more, like nice UI UX feature. User could see that is computing, and then you see the heat map here. And you could change the color scheme just by selecting a value from the dropdown. And here we have it, another heat map. Now we're going to have a look at the feature relationships. We're going to see how different numerical features are related to each other. It's essentially a scatter plot that we're going to show you here, and we've color coded them according to the bear species. And you're going to see that the brown bears are highly similar, and the American black bear is located here. This is with respect to the shoulder hump height and the body mass. So purely based on the physical characteristic of the bear here. And you'll see that I generated the code here using Snowflake Copilot. So essentially, just go here into Ask Copilot, connect your database and schema, and then just kind of vibe code parts of the code cell here, and you could experiment with that, and that would save you a lot of time in referring to documentation, finding the relevant code snippet, pasting it in here, or all of that good stuff. And here we have the feature relationship, essentially the same thing that we have here, but more interactive. You could select which feature you want to visualize, and it will compute the plot dynamically. Now let's have a look at the bear species class distribution. So you might have already known that we have 4 bear species, and each of them have the same number of instances at 50. And they are color coded right here. Let's do the same thing, but then using Streamlit again. And here you can select whether you want to have it a pie chart in addition to the bar charts. And you can look at other categorical features. You see that you could easily see which color are the most prevalent in your data. And how about the distribution of the facial profile or the paw pad texture? And very interactive directly in your notebook here. So if we aggregated all of the above together, we get this script. And so as you'll see, we are trying to print out the data sequentially, and then we're trying to print out the data visualization as well. But then as you'll soon see, it will clump together at the end. So the printed header is here, but then the images are shown at the end. Not very intuitive, so we're using the same thing, but then implemented in Streamlit. And it's essentially a data app inside your notebook. So all of that, 132 lines of code, and it helped to use Copilot to help me with creating this. So this process took a bit quicker than to do it manually, which might have taken a day or so. But with this Copilot, you are empowered to create, very complicated analysis fairly quickly. So we have this nice dashboard. This first segment provided the overview of the data. We have the summary stat and the plots here. And as always, it's very interactive. And this is part 2. So you already have created the data, you visualize the distribution of the data, and now we're ready to perform our model building. So we're gonna start part 3 here. Let's start it. So same thing, set up the external access and the relevant node compute pool. I have already done so. So if you're interested that you could rewind and have a look again, it's going to be the same steps as the one for part 1. All right, and so I'll show you here that we are pip installing the Snowflake ML Python library, which will allow us to track the models. Okay, so we're gonna first start by establishing a Snowflake connection. storing it into the session variable. Once it's done so, we print out the success message here. We're now going to load the data, the bare table data directly, and we're using Modin for that. And it's going to create a Snowpark data frame for you. And it's right here. Now we're going to prepare the data. We're going to split the data frame that you see into two parts. We're going to have the X variables or the independent variables, and then we're going to have the Y or the target variable, aka dependent variable. So the X variables will allow us to predict the Y variable. Now we're going to have a look at any potential missing data, which is not present here in our data. And we're going to perform data splitting. We're going to split as a general practice in machine learning model building. We're going to split the data into two parts, 80% part, 20% part. The 80% part will be used as the training data, where we're going to use it to build the machine learning model. Then we're going to apply that machine learning model in the prediction of the remaining 20%, which is the test set. And let's run it. But before doing that, we're going to also print out the basic summary statistics of the data split. So here we have from 200, 160 belong to the training set, 40 belong to the testing set, and these are the distribution according to the bear species. Now we're going to do some feature scaling, because different feature will have different scale, like the different minimum and maximum of each column. In order to make it easier for the machine learning model building process, we're going to standardize them. We're going to make the mean value for each of the column to be the same value, which is 0, and to have the same standard deviation value, which is 1. And we're going to do that by taking each value, minusing the mean value, divided by the standard deviation. And in doing so, you're going to convert each data cell value into a mean of 0 and standard deviation of 1. I mean, the entirety of the column will have the mean of 0 and standard deviation of 1. Sometimes you call that mean centering and also unit variance. Okay, so I think I've done so already, and it has the color green here. So we have already performed feature scaling, and these are the summary stat of that. Now we're going to build the model. We're going to build a logistic regression model. So we're using scikit-learn for that. And we are logging in the performance metric for the accuracy and the MCC, the Matthews correlation coefficients. So accuracy might be a bit popular as a performance metric, but I personally like MCC because it allows you to consider the imbalance of the data. But because this data set has perfectly balanced data class, there should be no issue with using accuracy. But if your data is highly imbalanced, using MCC is the way to go. So now we're going to build the random forest model, also using scikit-learn, and same, we're also going to track the accuracy and the MCC value. So for logistic regression, you'll see that it performed pretty good. Accuracy 95 for the testing set, 97.5 for the training sets. For random forest, the performance was a bit lower, but the great thing, it provides the feature importance where it's interpretable. The model is explainable. And let's have a look at the support vector machine. So support vector machine is like a black box where you can't see what's happening inside, and you won't know which feature contributed to the good or bad prediction. So in terms of this, I say logistic regression had a reasonably good balance of both. But random forest is great because it allows us to see the relationship between multiple features. Because it you could also generate a decision tree based on the random forest model. So that topic would be suitable for a more in-depth future video. If you're interested, let me know. So now we're going to benchmark, or we're going to compare the machine learning algorithms. And for that, we're essentially going to compute the difference between the training and testing performance. If there is a large difference, then it means that the model might not be performing well. And generally, I think it's like 0.2, where if there's a difference of 0.2 or above, the model is not performing well. So the difference between the training and testing should be roughly less than 0.2. And so for all of our model, it's well within that range. It's all less than 0.2. But as you see here, SVM, the testing set performed better than the training set, which is a bit not really trustworthy. So I would recommend using support vector machine. So yeah, positive value should be better if we're taking training minus testing. And now in terms of model interpretability, as mentioned, if you could gain insights from your model that will allow you to do actionable decision making process. And so logistic regression allows you to do that, and also random forest, because you'll be able to see the magnitude of each of the coefficients, the m value. So more magnitude means that, like for example here, the shoulder hump height is greatly influencing the prediction. It has the absolute value of 0.94, which is the most here in the data model. And if we want to plot this, we'll get this here. Feature importance plot for the regression, logistic regression. We're going to do the same for the random forest model here. But for the random forest model, it had its own different opinion, is saying that body mass is most important for the prediction process. Let's have a look at the plots. Right here. Okay, so I think it's not showing the proper label because we've set the color for actually the dark mode, but here you could adjust the color and it should show well here. There you go. So we have the features here and the importance value. And as mentioned already, SVM models are not explainable. They are like black boxes, so we can't gain essentially no insight from the model. Aside from that, it performs pretty good, but no insight, so I wouldn't use support vector machine. Also because it seems to be overfitting. So this concludes part 3 of the notebooks. Now let's have a look at the next part. Part 4. So in part 4, we're going to do the same thing essentially as part 3, but then we're going to add experiment tracking here. And you're gonna notice that we're using a container because it has this icon very easily. And if it has like a house, then you'll know that we're using a warehouse. If it has like a chip, then you know that you're using a container. So we have already clicked on start to start the container. You'll see that it mentions that it might take 3 to 5 minutes, but here is a lot faster than that. Definitely less than a minute or half a minute. As always, you want to set the external setting for your notebook, as already mentioned here, and in prior steps as well. So we start by installing the Snowflake ML Python library. And then, yeah, it's going to provide you the ability to track the experiment from the Snowflake ML. We're going to get our active session from Snowflake. We're going to filter out some warning that we might get. And then we're going to load in the data. And then we're going to convert it into a pandas data frame. And then we're also going to look at the basic shape, meaning what is the x, what is the number of columns, 11, and what is the number of rows, which is 200. So this is our data here. We're going to do the same thing. So essentially, let me show you this. We could just click on run all, and then it will run every cell in sequence here. Once it finishes with one, it will go to the next one. Okay, so no missing data as usual. And it's essentially the same thing as previously shown you. And we're performing feature scaling here, as already mentioned, to make it comparable. And we're encoding the target variable. So instead of having it as American Black Bear, we're gonna change it to like 0. And then the next one will be 1, 2, 3. So it will be changed to numerical value, which will be favorable for the scikit-learn machine learning model package to use for its prediction. As you'll see here, this is the encoded value for the training set above, and for the testing set here, we're going to write some data to a bear test data table, which we're going to be using for the experiment tracking model registry process. So here, we're going to perform experiment tracking setup, and we're creating a exp variable where we're initializing the experiment tracking, and then we're feeding it in the session variable for our current session. And then we're naming the experiment bear classification experiments. And then we're going to write out that it has been a success, that we initiated the tracking. Now, what's different here than the previous step was here we're also going to do hyperparameter optimization in subsequent steps. So here you'll notice that we're going to use fixed set of parameters here, meaning that we're explicitly using 100 number of estimator, we're explicitly using maximum depth of 3, etc. And these are the results. And if you like to have a look further for this particular experiment model, you could go to this URL. Okay, and it will allow you to see the tracked data. You see the accuracy value, the MCC from the run, the precision score, recall score. We see the metrics also here. We also see the parameters that was used, and then all of the associated metadata. While we're at it, let's have a look at the entirety of the bear classification experiments. So for each run and each logging of the data, which we've done so here, when we already initialized the experiments, what we're doing here is we're creating a run name, meaning that for each run, we're going to create a unique tracker for it. And we're going to assign the unique date, time, hour, the year, month, day, and also the hour, month, second. So that every time you run the model or with a slightly different parameter or tweaking of the parameter, is going to log everything into Snowflake. Here, it's logging in the metric, and it's logging in the parameters that we're using. And we see all of them at a glance. So these is the result of about 3 to 4 days of machine learning model building. And you see that most meaning 457 experiments had accuracy in the range of 0.92 and 0.93. So you see that getting reasonably good performance is fairly easy, but then getting really good results was a bit difficult, right? We have 31 count for the 0.95 to 0.96. And here you could change the performance metric, and you see the distribution. And this is without code. So you could just go here to the AI ML and then click on experiments. and then you click on the bear classification or the experiment that you created. And it also has a summary table, and you could click on it to sort the data. So all of this is really helpful for you to decipher which combination of hyperparameter or algorithms are best for your use case. So here we're doing a hyperparameter tuning where we're going to use a list of values, and you could expand the list here, but then expanding the list means it's going to take a lot longer. Um, Not really a lot longer, but exponentially a lot longer. Because if you have two values here, and you have two values, and you have three values, and two values, it means that your model is essentially 2 times 2 times 3 times 2. So you have 24 possibilities. So it's going to do all 24 possibilities for you. But if you have 5, it will be more exponentially higher, and it will take a lot more time for you. So this very minimalistic set of parameter took about a minute to compute. And for each calculation, it gets its own experiment page, as I have already shown you. And you see that there's a slight permutation of the hyperparameter shown here. And then you could look at the data frame, and then we color coded the data frame according to which parameter provided the highest performance based on the accuracy. And several models provided that. But the best model configuration was selected to be the random forest with the n estimator of 100, maximum depth of 3, minimum sample leaf of 1. So it's selecting the like the least computationally intensive parameter set that yielded roughly the same accuracy results. So that will allow you to calculate faster. Once that is done, once we have the best model, we're going to save the best model, run it for the final time, and then take that final model using this optimal set of best parameter from our hyperparameter tuning experiment. And now we're going to deploy the model. We're going to register the model into Snowflake's model registry. And we're going to import here, Snowflake ml.registry, import registry. We're creating a registry variable here. And then we're giving it a model name of bear species classifier model version. And then we're essentially saving it into Snowflake. And here we're saving it as bear species classifier. And if you use a SQL statement like show models, you'll be able to see all of the models that are in your workspace. So here we have a few. And this was using SQL, and this is using Python. Same result here, and show available versions in the model, because when you're building, experimenting, tweaking, you have a lot of data in here, a lot of versions of the model. And for each model that you registered on the registry, it will here using show functions will allow you to see what are the possible functions that you could do with the model that you have. So here we could use decision function, we could use predict, we could use predict log probability, etc., predict proba. And that's, I think, almost okay, we're almost ready there. And then we're going to deploy the model as a service. Okay, so before here, prior to this, we've run our hyperparameter tuning. We got the best model. We registered the best model into the Snowflake model registry. Then we're going to deploy the model from the registry by creating a service. And we're creating a service called Bear RF, RF standing for random forest classifier. And then we're using a system compute pool, the CPU pool here from the Snowflake container service. And then we're going to create a service called Bear RF classifier. So once that's done, we're going to have a look at all of the services that we have access to. So you'll be able to see that the Bear RF classifier that we just created is currently running. And these are the details of it. This is where it lives. We scroll down. We could have a look at the endpoint. So this bare RF classifier is now a REST endpoint that you could use to embed in your data app, which we're going to do in the next step, the next and final step. But as an example, before we proceed further, we're going to have a look at how you could actually use the model that you deployed just a few moments ago by providing the data value for the data columns here. We provide the body mass, shoulder hump height, claw length, etc. here, all of these. And then we're taking all of the value from the bear test data that we created just a few moments ago to make a prediction. And so here is making a prediction. And the output feature 0 here is that for the first row of the example data table of the bear test data, is predicting the bear species to be 0 and the bear species to be 1, 0, 1, 3. Okay, so in the next data app, we're going to actually see which corresponds to the species. Like if 0 is the American black bear, 1 is, for example, Kodiak, etc. And this might be helpful for you to have a look at um, like performing some summary statistics and have a look at the average value for each bear species. For American black bear, it normally has a body mass on average of 144 and etc. here. This might be helpful when you try out the next app. So here we're going to go to our project, click on Streamlit. We're going to go back to our repository here, and then we're going to click on the bear prediction app. And what you want to do is click on raw, and then you want to select everything, Control A or Command A, or just right click and then select all. And then we're going to copy it just to make sure, or you could just Command C or Control C for that. And then we're going to create an app. So once we click on Streamlit, we're going to click on plus Streamlit app. And now we're going to select the database. As already mentioned before, we're going to use Chanin demo data. I'm going to run this on a container. And I'm going to say create. And the app should be spinned up in a few seconds. So I've deleted the original example data app here, but it's still loading it because I haven't saved it yet. Just leave it here first. Once the app is loaded, then we're going to replace it with the one we copied from the GitHub repo. All right, so now we are going to replace the app and we're going to run it. And this is our app. This is the bear species prediction app. To the left side here, you're going to get the sidebar, which allows you to select the model. We just created the bear RF classifier service, prediction service as a REST endpoint. And then here we could explicitly select the physical measurements of the bear and the categorical feature, which color of the bear here. And then click on make prediction. And then the main part of the app will make a prediction. As you'll see, it took 0.71 seconds to make a prediction. So we're not performing model building, but we're just feeding in the features that we provide here as a user, the numerical feature and the correct categorical feature. All of them will be feeded into the app, and then we're going to prepare a data frame, essentially prepare a data frame here, and then feed that data frame into a SQL statement that will make a prediction. Here, select, and then based on the model that you selected from the drop down here, it will make a prediction. And using the data from temp view, which is the temporary data that we have here. And depending on the features that we selected, you could play around with this. Let's see if we get a different bear. We have a Kodiak bear. But I guess the Kodiak bear is the most prevalent. And the model is predicting it to be the Kodiak bear. And that's essentially all that we have for this workshop. So, in a nutshell, let me go back to the first notebook. So, in a nutshell, you've already performed ingesting the data, performing AI powered data preparation to extract categorical features from your image data, and then we combine them together, save it to data into a data table on Snowflake. Then we perform exploratory data analysis to get more insights on the data. We built some machine learning models, then we experimentally track the models, and then we deploy the model, and now we embed that deployed model service into the interactive data app using Streamlit. And as you'll see, we also embedded Streamlit in every part that is possible here to make the UI UX a bit more user friendly. And as already mentioned in the presentation, all of the data code and also the guide is provided here via the QR code. And as always, you head over to the Snowflake documentation. This piece of article on Snowflake ML end-to-end machine learning is a good read, and I highly recommend it. And yeah, thanks for following along in this tutorial, and happy coding.